Namaskar and welcome to episode number 8 of Understanding Feynman's Physics podcast. Yesterday's dilemma of magnetic field being the relativistic effect of the electric field is very fascinating. I really got fascinated by it yesterday, and so I decided to really get into it and understand it through some videos on YouTube, especially done by a combination of, not a combination, a collaboration of Veritasium and Minute Physics, two of my favorite channels. Earlier, I had not understood it. Earlier, when I saw that video before, it was a little confusing. I'm not really very comfortable with it yet. I wouldn't say, but I'm more comfortable with it. I understand it more because of Feynman's way of explaining. I'm sure there are better other people who can explain things, break things down very easily. But the thing with Feynman is that his way of explaining is just very tantalizing. I don't know. There is something about his way of explaining it. It's, I think, to do with the first principle way of thinking about things. Feynman used to use his own terminology, his own um, symbols in equations, his own names for phenomena, and he would not be worried about being he didn't care about the status quo, even when he was at the top of it. He was an acclaimed, highly acclaimed physicist. Everyone around him loved him and looked up to him. But he never left his childlike charm of physics. One of his stories is about asking. He was trying to study zoology. Zoology, how you say it? I've only ever seen it written down. But so he was studying zoology, and he wanted to understand what a cat's interiors are. So he went to the library and asks the librarian, "Can I have the map of the cat?" And that should tell you everything about what I'm trying to say. He would not be scared of terminology. He would go back down into the meat of things. But anyway, enough about that. Let's go back to the topic at hand. The relativistic the relativity. No, if you have never read relativity, if you have never came across what relativity actually means, well, it it's it can be complex. It's not easy. It's not very easy to understand mathematically. But I can tell you a few things about it, which can be really weird. If you see someone moving at a very high speed, they will appear shorter to you, right? And they would age less according to you, or something like that. I'm always confused. The fact is, I'm confused about relativity a lot of times because it's very it's confusing to me. It's not very intuitive, of course it's not, but But in this sense, in this way, in this manner, in the manner of magnetic field, I kind of do understand it. Yesterday we talked about the fact that two wires going parallel wires will exert if there is current flowing through both of them, they will exert a magnetic force between each other, right? But if you're just standing still and compared to you, the charges are moving through the wire, and I'm trying to explain why they would attract or repel each other based on whether the current is going in the same direction or the opposite direction. I don't remember which one is which, but so if you're standing, you see two wires in front of you. Both have electrons flowing. From your point of view, the electrons that are flowing will create a magnetic field, of course, right? Flowing electrons create magnetic field. And the other wire also has a moving electron, and a moving electron in a magnetic field will feel the force of the magnetic force, what we think when we are standing on the side, we think it's magnetic force, right? However, if you move in the direction of the electrons yourself, which you can actually do very easily because the electrons are moving at a very slow speed, a few centimeters per second, we can actually move faster than the electrons in the wire. But they are moving, and you can move with them in the sense that in a way in which you do not feel, from your point of view, the electrons are not moving. In that case, you would see that so this is what's happening. The wires are made of electrons and protons. When you see that when you are also moving along with the electrons in the wire, the positive part of it, the positive charge, the protons in the wire are moving in the opposite direction according to you. So you will feel that they take up less space because of relativistic effects. Because if you see something moving from your point of view, you see that it takes up less space. So if protons are taking up less space, which means more are packed in a smaller space, and which means that at any point on the wire, it will be, if you're moving along with the electron and the protons are not moving, you are experiencing a denser positive charge, and the electron in the other wire will be also feeling the same thing, will also feel a denser positive charge in the other wire, which means it will get attracted towards it because it's negatively charged, and then it will attract or something like that. So the point is, the details are a little confusing. What is positive, what is negative, repelling, attracting, this and that. But it's now more clear in my mind that magnetism is relativistic effect of electricity. I'm not very convincing. I know you might be listening to me and thinking, he truly hasn't really understood anything about this thing. But yeah, you'll be right, I guess. But And that's the point of this podcast. I lay bare my ignorance and difficulty in understanding something in the hopes that I find travelers in my journey who do not get scared by new things, and who do not get scared by ideas they don't understand, and just push through, just figure it out. If even if you don't figure it out, it's fine. You get a little picture of it, you get an understanding, and you want to move forward and maybe come back to it later. That's fine. And this is what I'm going to do. Even if I don't fully understand every aspect of it, I kind of get it. I get it. I get how. Wait, one more thing which is important is, you might say, uh, the charges are moving at 1 centimeter per second. What kind of relativistic effect is that? I thought relativity works in really high speeds at the level of 90% speed of light, 99% speed of light. It's perceptible to us. Otherwise, it's not really perceptible to us. It's very, very small. But the thing is, even if it's really small, the difference in charges between the different in charge density between positive and negative, according to you, if you are moving along with the wire, is very minimal. The charge density difference between positive and negative is very, very less. Very, 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 very less. But it's still there. And this is where you understand the power of the electric field, the strength of electric repulsion and attraction. Even that tiny, 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 tiny difference in the density can create substantial force compared to the gravity of our planet. So much so that it can move objects and pick up objects with that just this tiny force. And it shows to us as this magnetic field that can pull big metal objects towards other big metal objects. Right? Fascinating, right? It's really fascinating. I love it. The chapter has ended, the first chapter in this book, the book number 2, with this beautiful paragraph. The final paragraph of the book is really nice. It tells us about how, when the first time Greeks figured out that there is something strange about rubbing 2 pieces of amber, and it can lift up some pieces of papyrus. And then there is this strange rock from the island of Magnesia, which attracts iron. And that was the only way into the electrical world for the ancient people, not ancient people, but ancient Greeks, the Greek people. They thought that that's some esoteric force. It is, as it turns out, everything, every part of the body, we work because we are functioning. Our brains are functioning because of electromagnetism. Our neurons are electromagnetic in nature. Our brains sense the world through this force of electromagnetism, and this is all around us, and it's really fun to understand and figure out. And there are these very interesting paragraph. This is why I love Feynman. I'll just read this paragraph so that you also get the beauty of it. Today we are applying even more subtle effects. The electrical forces, enormous as they are, can also be very tiny, and we can control them and use them in very many ways. So delicate are our instruments that we can tell what a man is doing by the way he affects the electrons in a thin metal rod hundreds of miles away. All we need to do is use the rod as an antenna. for a television receiver. You see what happened? The paragraph ends, but you see what happened? He explained this amazing phenomenon, saying that so delicate are our instruments that we can tell what a man is doing by the way he affects the electrons in a thin metal rod hundreds of miles away. You would think, what kind of an instrument is this? What kind of an amazing instrument is he talking about? Is he talking about some extremely expensive millions of dollars of equipment, electron microscope or whatever? No, he's talking about the television antenna. See how he talks about science, how he treats science, how he treats people. Amazingly, he takes this mundane phenomenon of television. Everyone knows about the antenna. You fix your antenna. I have spent my childhood doing that in my home. The antenna that we had, we would mess it up. I think I'm betraying my age here, but yeah, that's the what's happening is the electrons in that antenna are being tilted by the distant transmitter of the signal of from television. Beauty, just love it. Love Feynman, my hero, our hero. Thanks for listening. See you tomorrow with a new chapter, new way. Not tomorrow, maybe day after or whatever, but with a new chapter, a new day, a new life. Enjoy.